So, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. So, welcome to a new class on digital signal processing. Today, we are going to cover, I plan to cover or introduce multiple topics. So, we would try to be very comprehensive, but we would not be less rigorous. So, let's see. So, the first topic that I want to cover briefly today is the frequency transformations. So, up till now, what we have done is that we were given this specification of this low pass filter, but and we were designing the low pass filter with the knowledge that we can transform any filter from from the low pass to the high pass, from the low pass to the band pass, and from the low pass to the band stop filter. Right. So typically, you have for a digital, you have this omega p1, delta p, and then you have these frequencies of the stop band WS1, WS2. ठीक है, अगर फॉर एग्जांपल आपका एक मल्टी बैंड किस्म का फिल्टर है तो उसकी स्पेसिफिकेशन इस तरह से आपको दी गई होंगी WP2 एंड देन पाई फॉर इंस्टेंस. ठीक है, सो स्पेसिफिकेशन ऐसे दी जाती हैं. एंड नाउ व्हाट वी आर लुकिंग एट इज कि हमने तो अभी तक लो पास फिल्टर पढ़ा है, और how can we transform our filter into a different kind of a filter, which is high pass, band pass, and band stop. So the usual process that we have up till now followed is that you were given digital specs. That means you were given this omega p, omega s, delta p, delta s, and from that you change the specs to analog. Right. For example, there was a tangent formula, right? So these frequencies were related to each other through tangent of omega p by 2 for the BLT transformation. There was a linear connection between these frequencies, analog and the digital frequencies for the IIT transformation. So you use these specs you converted these transformations to convert the specifications into the analog specification, and then you designed these analog analog systems, and then you converted through BLT or IIT transformation, you converted these to digital filters. So now if you want to convert that, how can we go about this? So we can first convert, for example, this low pass analog filter into another type of filter and then convert it back to the digital. That can be one option, right? But the option that we would study today is that we would study digital to digital transformation. That means we would be given digital specs, we would have a digital transfer function, and we would study a digital transformation so that we have another kind of a filter. So what we are going to study is digital to digital transformation. So in digital to digital transformation, you are given a digital. What is happening today? I don't know.
सर वो इंक टू शेप ऑप्शन है ना ऊपर, वो हाईलाइट हुई है, अगर उसको
That's fine.
नहीं. यस सर.
Okay, very good. Thank you. Okay, so we would be given this digital discrete time low pass filter, we would call this h of capital Z. Okay, so the capital Z, please note कि हम इसको इस तरह denote करेंगे, and we would transform this digital discrete time to the desired discrete time desired filter, and that would be h of small z. So small z, I would be represented like this. And this transformation would be such that it is easier to do the transformation of z inverse rather than z. So the transformation would be such that z inverse, capital Z inverse would be some function g of small z inverse. And if this is your h low pass of capital Z, your h of z would be equal to h of capital Z such that z inverse has been transformed to g of small z inverse in this filter. And this way we can do this transformation. Is it clear? ये notations आपको clear हैं?
Yes, sir.
Okay. So there are some rules, right, constraints on these transformations. And the constraints are, number one, that g of z inverse, this function, must be a rational function of z inverse. Small z की बात हो रही है यहाँ पे. Inside of the unit circle of the capital Z plane, should map to, must map to the inside of a unit circle of the small z plane. And the third is that unit circle of the z plane must be mapped to the unit circle of the small z plane. Should map to unit circle of z plane. So these are the constraints. And from the last constraint, okay, and the frequency of the capital Z plane would be kept theta. Theta would be used as a frequency variable. For h of capital Z, and omega is the frequency variable for h of minuscule z. And that's for the condition 3 to hold, e to the power minus j theta must be equal to g of e to the power minus j omega mod. Remember, the transformation is g of z inverse. So g of z inverse, where z, capital Z inverse, that is e to the power minus j theta, must be replaced by small z inverse, e to the power minus j omega. So this is the transformation. Right? And because these must be equal, this guy must be equal to 1 for left hand side to be equal to the right hand side. So if a complex number or in the polar coordinates, two complex numbers are equal, their magnitude and the phases must be equal separately. So this magnitude response must be equal to 1, and minus of theta must be equal to angle of g of e to the power minus j omega. So this means that we are talking about some all pass transformation. And all pass functions or all pass filters appear very often in digital signal processing. So there was a PhD thesis of a Greek student, Constantinitis, who in his PhD thesis he proved all of these digital transformations, and notations are still followed through his thesis. जो भी उसकी thesis के अंदर इस्तेमाल हुई थी वही चल रही हैं. So he proved, right? So there are proved that you can do in generic transformation, generically all the transformation can be represented like this. So a generic function, if you want to write, is, let me take this further down. My estimate of the writing is not accurate. So generic function that he suggested was that this transformation would be of this form. Z inverse would be equal to G of small z inverse, and it would be of the all pass form, summation k equals to 1 to capital N, and it can have different signs depending upon what transformation is being done. Z inverse minus alpha to the power alpha k over 1 minus alpha k z inverse, where alpha would of course have different values. And this equation one would satisfy the constraint to inside of the unit circle must map to the inside of the plane if and only if alpha mod is less than 1. So this means that alpha mod is equal to 1. So he proved that only then constraint 2 can be satisfied. Okay. So now let's look at low pass to low pass transformation. So what you can do is you have this h of z, it is a low pass filter, and you would transform it to one low pass filter that would have a separate different omega p. Second, you can transform it to high pass filter. Third, you can transform it to a band pass filter, and fourth, you can transform it to band stop filter. So low pass to low pass transformation says, and remember the frequency variable here is theta. Theta p would be the pass band. Frequency variable here is omega, and omega p would be the pass band frequency. And that Greek scholar said that low pass to low pass transformation would be Z inverse. It would be the first order. Z inverse minus alpha, 1 minus alpha Z inverse, where alpha would take this value, sine of theta p minus omega p over 2 divided by sine of theta p plus omega p by 2, where omega p is the desired cutoff frequency. And using these two equations, you can prove, I did the proof in my notes, but I would not do it for the sake of time, that you can solve it for omega. It's not very difficult, but it is a little bit involved. This can you have to represent these form into sine and cosine, and then take the ratio to represent that into the tangent form, and then take the tangent inverse. So half page derivations. You can represent omega, you can find omega from these two, where omega is tangent inverse of 1 minus alpha squared sine theta divided by 2 alpha plus 1 plus alpha squared cosine of theta. Hence you have everything. Now you are done with the transformation. You need this alpha basically. Given these theta p and omega p, you need to find this alpha and you're done. You have this transformation. Okay. And you can, this figure here is for the low pass to low pass transformation, where different values of alpha would change to different values of theta p would change to a different values of omega p. So for example, omega p, theta p is there. This is the cutoff frequency. You can see the cursor? Yeah. So this is your theta p, but this theta p can change to this theta p, and this theta p, depending upon your alpha. Of course, alpha is equal to 0 is the linear line. So theta p would be equal to omega p. But depending upon alpha, positive or negative, alpha can be negative. So positive or negative alpha, for different values of alpha, you can have different values of the cutoff frequencies. Right. So this graph is interesting in that sense. And this table below shows different transformations. So if you want to do a low pass to low pass transformation, your transformation is given by this. And if you want to convert that into high pass, all you need to do is to change z by minus z. And so this book has taken the same notation. Same notation as taken by the constantinitis. Otherwise, you could have the same value of the z inverse, same value of the, you can have the same z inverse, but a different value of alpha. But nevertheless, this is how your transformation works. So z inverse minus alpha over 1 minus alpha z inverse would be as low pass to low pass transformation, where alpha is given by this, and it would transform. Once you transform, you get your h of z with this transformation. Now your new omega, your desired cutoff frequency would be omega p then. Okay, for a desired cutoff frequency to be omega p, you need an alpha. In other words, for a desired cutoff frequency of omega p, you need a alpha equal to this sine of theta p minus omega p over sine of theta p plus omega p. So you can see that low pass and high pass are very similar to each other. There is only a minus sign that is different, and that is always the case. In the digital signal processing, you just change the sign and you get a high pass filter from a low pass filter's h of z. So that's it about the transformation. So you have these formulas for band pass and band stop transformation. So your knowledge about these transformation is complete. It's not a rocket science. These are just transformations. There is no proof in the textbook. There is no proof anywhere. You need to know, however, that you can transform any low pass filter to any other kind of a filter using these transformations. Any questions about this?
No, sir.
Okay. So now let's move on to FIR filter design. So in IIR filter, we had these analytical formulas for the Butterworth filters order and the Chebyshev's filters order. So we can have those analytical formulas, but you cannot have these analytical formulas for the FIR filtering. So the reason why we go towards FIR filter design is that FIR filters have two important properties. One is that they are stable. They are called unconditionably stable, but implied is that your finite impulse response must have a finite amplitude. Of course, any amplitude going to infinity would make it unstable. So we call them unconditionably stable. They can be made causal. Causality is not a problem. So realization is not very difficult in terms of causality, right? So you can just shift the filter to to make the filter realizable. And the third and the most important point is that FIR filters can guarantee linear phase response. And linear phase is important, right? Why linear phase is important?
So we get an output which is not distorted.
We get we get an output which is not distorted. Uh, in other words, we have something that is uh, distortionless or delayed version of the signal. और group delay जो है वो constant आता है इनका. ठीक है? All of these mean the same thing. ठीक है? Okay. So design of the FIR filters is done both typically done by computer aided design, लेकिन we can have some feel of these filters, and these kind of design are sometimes called semi-analytical designs. Through which you can get a rough idea of what your filter is. So FIR filter, you cannot guarantee any specs. So you would just design a filter, then you would check the frequency response of the filter, whether or not it satisfies. If it does not, you increase the order. So that is how it works. But semi-analytical filters, semi-analytical designs allow you to get some idea of what the order should be. And there have been people in the Bell Labs, those who have developed formulas. So given the specs, you can get a rough idea what the FIR filter order should be. By the way, order of the filter just means the number of terms in the FIR filter. So those formulas are available, right? So I'm not going to write it here, but they would give you a rough idea. They would never give you an idea that is concrete, that this is the order that is going to work for the FIR filters. But nevertheless, we would do this semi-analytical designs. One of them is windowing. The other is called frequency sampling. So today we're going to study FIR filter design through windowing, and hopefully we would also try to incorporate the discussion of the linear phase FIR filters and their different types. So let's see how can we go about this. So the idea of the FIR filter using windowing is very simple. That suppose you have a desired transfer function, right? Given you have a desired transfer function, and with the desired transfer function is hd of e to the power j omega, and you represent this hd of e to the power j omega using the inverse Fourier transform, using the Fourier transform analysis. It would be summation n equals to minus infinity to plus infinity, the impulse response times e to the power minus j n omega, right? This we know. These are the different types of windows that we would see today. So of course, this is your ideal impulse response, but this is not an FIR response. So this is an IIR response. So the idea of the FIR filtering using windowing is to just approximate this HD of e to the power j omega. So we would truncate this HD of n arbitrarily and hope that it would work. So that is how it works. So you would arbitrarily trunk it to a length of m plus 1, and you would hope that it would work nicely. Right, so you can truncate it from n equals to minus m to plus m, for example, but that again causes the problem of the causality. Typically, even the truncation is done from 0 to a particular value of m. So what you do is you would truncate it from 0 to m. Right? So this is what is called windowing, right? So you would say that the age of e to the power j omega, we would say that would be approximately equal to hd of e to the power j omega, which is given by summation n equals to 0 to capital M hd of n e to the power minus j omega n. So as if you have multiplied your hd of n, your ideal hd of n, with a window of size capital M. Okay. So you can write it as your h of e to the power j omega is equal to summation n equals to minus infinity to plus infinity h d of n e to the power minus j omega n, but you multiply this with a windowing function. So you would multiply your h d of n with a windowing function w of n, and your window of n in this, for example, one of the possible windows is that it is equal to 1 for n between 0 and m, and it is 0 otherwise. So this is the so-called rectangular window. And the so-called rectangular window has abrupt discontinuities, right? At n equals to 0 and n equal to 1, it has abrupt discontinuities. And we know the problem of this abrupt truncation through a famous phenomena, which is called the Gibbs phenomena. So we know the problems of a rectangular window. We know that an abrupt truncation of any signal leads to the so-called Gibbs phenomena, where if you recall from your discussion of the Fourier series, that if you approximated your Fourier transform of this, if the rectangular function should be the Fourier transform of your signal, for example, in the time domain if you have sync, and if you have truncated your sync function, what happens is that you would have some and these overshoots and this undershoot right after at the point of discontinuity is significant, and it does not decrease even if you increase the window size. So that is the problem, right? So this is what is called the Gibbs phenomena, that this overshoot is always going to stay. This overshoot is always going to stay, and this is approximately 18%, right? Approximately 18%. So this is significant. So rectangular windows has its problem. It would lead to this what is called the Gibbs phenomenon. So how to select a window? So that is the question. So let's start with, again, let's look at this formula. H of e to the power j omega is equal to summation n equals to minus infinity to plus infinity h d of n w of n e to the power minus j n omega. ऐसे ही है, where w of n now can be anything, is non-zero, can be non-zero, it can be zero as well, for particular points between 0 and m, and 0 must be 0 otherwise, mean n greater than m. And then we do something that we have been doing very often. We would apply the definition of hd of n here. So that would be equal to summation n equals to minus infinity to plus infinity. hd of n can be written as 1 over 2 pi integral from minus pi to plus pi hd of e to the power j theta, because omega is already used as a variable. So let me choose another dummy variable, e to the power j n theta d theta times e to the power minus j n omega. Okay, and because of the linearity of these integration and summation, we would interchange the order. We have done this many times in our signals and system course, so it's a usual practice. If we
तो
interchange
ओमेगा एन भी
order,
मल्टीप्लाई होगा ना सर?
sorry,
तो ओमेगा एन भी मल्टीप्लाई साथ होगा, डब्ल्यू एन.
जी, WN would be here, yes. Thank you. If we interchange the order, it would be 1 over 2 pi integral from minus pi to pi h d of e to the power j theta is not a function of n. Summation n equals minus infinity to plus infinity w of n e to the power minus j n minus theta. सही हो गया? d theta. But this inner term we can write it as, कैसे लिख सकते हैं इसको? So that would be equal to 1 over 2 pi integral from minus pi to plus pi h d of e to the power j theta. So this is जी
सर एक्सपोनेंट पे थीटा माइनस ओमेगा एन नहीं होगा? थीटा माइनस ओमेगा एन.
यहाँ पे एक्सपोनेंट में कह रहे हैं, माइनस जे भी तो है ना, माइनस जे.
सर क्योंकि दोनों में एन है ना, तो एन कॉमन हो जाएगा और थीटा माइनस ओमेगा हो जाएगा.
जी अच्छा, हमारे पास e to the power j n थीटा है, हमारे पास जी n कॉमन है, n कॉमन है, we have n is common, minus j omega minus theta n, ऐसे ही है.
यस सर.
बिल्कुल सही है, बिल्कुल सही है. और now it makes sense, क्योंकि उससे पहले तो ये it was difficult to judge what it would be. So it would be what? It's simply e to the power j omega minus theta. ठीक है, it's just a Fourier transform, a discrete time Fourier transform of w of n, where omega has been replaced by omega minus theta. कह सकते हैं ना इसको हम?
यस सर.
d theta. And hence we can write it as 1 over 2 pi integral from minus pi to plus pi. This is nothing but periodic convolution अगर आप देखें. So because periodic convolution is commutative, so you can write it as W of e to the power j theta hd of e to the power j omega minus theta d theta. Or this is your h of e to the power j omega. And now we can think of what window here would give us the best approximation. Right? So remember, this is an approximation. हमने इसको truncate करना है. So कौन सी window would give us a best approximation? So this is a periodic convolution between w of e to the power j omega and hd of e to the power j omega, and we know that we would get hd of e to the power j omega exactly equal to h of e to the power j omega if, right? So we'll get exact h of e to the power j omega if w of e to the power j omega is what? किस चीज से कन्वॉल्व करें तो एग्जैक्टली वही चीज आ जाती है.
One. So
it would be an impulse function. So if we have this impulse function, however, this would mean that your w of n equals to 1 for all n. So this, in a way, it's the trivial solution. But nevertheless, it tells us that what we want is in the frequency domain that our window must have a frequency response that should approximate a delta function. And in a way, it is giving you a 1 for all n. It's not FIR, it is an IIR. But nevertheless, we would try whatever our FIR filter is. We should try to approximate it. It should be something similar to a delta function. So आपकी window का जो भी frequency response होगा वो इस shape का typically होगा. Right? So you would want, in order for this to approximate delta, this main lobe width must be as low as possible. Similarly, this side lobe height must also be as low as possible. So that is what you desire. You desired something that is similar to this function. By the way, the rectangular function has a frequency response similar to this, but it has a very sinc function, decays very slowly. So it has a very high side lobe ratio as well, and it results from the Gibbs phenomena as well. So that these are the two problems with the rectangular window. Nevertheless, it is one of the windows that would be used for comparison, at least that would be shown for comparison. In practice, it may never be used, but it would be shown here for the analysis. So for the comparison. So this is your this should be your frequency response, by the way, w of e to the power j omega. But these requirements, that means you want a main lobe to be minimized and your side lobe height must also be minimized. These two are conflicting requirements. These are conflicting requirements. And you see these conflicting requirements everywhere. In engineering, these are engineering trade-offs, right? And this, for example, in this particular case, this is because of the time frequency reciprocity. You can increase the order or the length of your filter that would do what? That would reduce uh, the side lobes, but that would increase the expand. So you can reduce the side lobes at the expense of the main lobe addition. Okay, so that is the main trade-off. So if you increase the order, your you would see that if you increase the order, your side lobe height gets decreased, but your main lobe width gets increased. Okay, so now we can look at different windows. ठीक है, जो कि लोगों ने propose की हुई हैं. So one of the windows is what is called the rectangular window. A rectangular window, it is equal to 1 for n equals to 0 to m, and it is 0 otherwise. So there are other windows as well. So this Bartley window is a triangular window, so in which you increase like this. Then you have this Hahn window, in which you have 0.5 minus 0.5 cosine of 2 pi n over m. So it is something like this. But this window, Hahn window, has a problem that for a order of m, for a length of m plus 1, the first and the last taps are 0. So while you are using m, so your textbook calls m to be to be the order of the filter, but the length is m plus 1 here. So it depends. So different textbook have different notations. So we'll stick to this m notation. So for mth order FIR filter, you effectively जो आपके taps हैं, that those are m minus 2. 2 taps आपके 0 हैं, वो आप use ही नहीं कर रहे हैं, ठीक है? So that is one of the problem. Not a problem, but it's one of the features of Hahn window. So Hamming said that we can use this in a different weight vector. So 0.54 minus 0.46 cosine of 2 pi n over m, and that would mean that you would be making use of the all the taps. So these taps, the first and the last tap, would not be 0 anymore. And you can see that if n equals to 0, you would have a w of n would be 0.08. And then Blackman said that why you are restricting yourself to the first order, first harmonic of the cosine function, why not use the second harmonic? And he presented in some order a window, okay, cosine की दो harmonics को ले रहा है, ठीक है? So that is how these windows are, right? So all of these are smoother windows, right, compared to the rectangular windows. So if you can see here, you have this rectangular window, जो कि सबसे ऊपर है. This is your rectangular window. And then you have these Hamming, Hahn, Blackman, and Bartley windows. There's hardly anything, lot of things to choose between these windows, but people have different opinions about. So their frequency response also becomes important when it comes to there's a filter design, because you're designing filters. So frequency responses are important. Any questions about these windowing FIR filter design through window? So if we focus on I would recommend you, I would not, let me not plot all of these. I would recommend you to do these comparisons of different windows, Fourier transform, Fourier transform. That is on page 561. Rather, let me show you here. So so what happens is it's the same kind of a phenomena. So first look at rectangular and Bartley. So if we compare the frequency response of the rectangular and Bartley, you can see that your M is 50, M is 50. So your rectangular window has very high side lobes. That is -13 dB से इसके side lobes start हो रहे हैं. देख रहे हैं आप? This line
Yes,
is
sir.
-13 dB. और इसके side lobes are significantly lower. ठीक है? So one thing is कि आप side lobes आपने reduce कर लें using a Bartley window. ठीक है? Now let's look at other responses as well. So now you can see that for a hand window, आपके जो side lobe हैं, it is around minus, side lobe decrease हो जा रहे हैं, ठीक है? तो this is now further reduced, this side lobe ratio, and then here it is further decreased by the Hamming window. Further decreased by Blackman window. So these are the analysis. अच्छा, जो मेन लोब की विड्थ है उसमें उसका ट्रेड ऑफ अगर आप देखें, so मेन लोब की विड्थ सबसे, you want to approximate this to the impulse response. अब मेन लोब की विड्थ, जहां साइड लोब कम कर रहे हैं आप, अब मेन लोब की विड्थ और करें. This is very close to 0.2 here. This is not very close to 0.2. ठीक है? So first compare the main lobe width of rectangular and hand Bartley. So जो rectangular है इसकी main lobe width बहुत थोड़ी है. Probably the best in terms of the main lobe width is rectangular. ठीक है? लेकिन उसके side lobe इतने ज़्यादा हैं कि वो it is hardly ever used. But so you can use other windows with a slightly higher order to get a similar main lobe width. Right, so these are the trade-offs you would always have in the engineering design. Any questions about, any comment about these windowing, FIR analysis using windowing? Another window which is very important is Kaiser window. Okay, Kaiser window has a complicated looking function. It involves Bessel function, and it is typically, Kaiser window is better than these windows. Kaiser window is typically used a lot. It is used a lot. So I would recommend you to go through this at least. So you have the expression of the Kaiser window on page 566 of the textbook, and the corresponding time domain and the frequency domain picture for different values of the beta, because there is a parameter beta in the Kaiser window. Changing that parameter would change the shape of the Kaiser window. So it's a very important window. Kaiser is used a lot. Kaiser window. Right. So uses I naught of beta, where beta is the parameter that controls the shape of of hd of n and h of e to the power j omega, both. So it's a function of, it involves Bessel function. It involves Bessel function. Okay, see. So one thing that you must have noticed is that all of these windows are symmetric around m by 2. यानी अगर आपका ऑर्डर m है, m by 2 के क्रॉस जो है that is symmetric. इसकी कोई वजह समझ में आती है? Why do we want this to be symmetric around m by 2? F. What would be the phase response of this system? Okay, what would be the phase response of this window?
Squared.
इसका क्या phase response होगा?
The sync squared.
हाँ, and it would be zero phase.
Yes.
It's real and even, it's zero phase. ठीक है? अब आप इसको shift कर देते हैं and you keep it symmetric around m. ठीक है, तो क्या हो जाएगा? Shifted version हो जाएगा, or it would guarantee a linear phase response. So remember, we are talking about linear phase. One of the most important reason that you would come towards FIR filter design would be the linear phase requirement. Otherwise, in terms of hardware, space, and complexity, or the size, IIR filter designs take less of a hardware compared to the order. यहाँ पर FIR के केस में बहुत ज़्यादा होता है, ठीक है? The same thing that you can do with 3 or 4 fourth order IIR filter, you need an order of more than 20 for FIR. But this linear phase response thing is something that is so important. So now let's look at the linear phase FIR filters. That is again one of the most important, one of the important topics of today's lecture. Okay. So we would talk about linear phase FIR filters, and to start with, we build our motivation that if our signal is non-causal, for example, non-causal is an option. If you have a real and even function in time domain, then it would have a zero phase response. Okay, the frequency response would also be real and even. So if the frequency response is real and even, this means it has a zero phase filter. Okay, technically speaking, zero, it can be negative, and hence you can have phase changes of plus minus pi radians. ठीक है, ये चीज नोट कर लें क्योंकि दिस इज इंपॉर्टेंट कंसिडरेशन. फेज के अंदर प्लस माइनस पाई की जो चेंजेस आती हैं, इट इज वेरी इंपॉर्टेंट एंड मस्ट बी thought through. We should not ignore these phase changings of the phase. The linear phase FIR filters must obey either the symmetry or entry symmetry of the impulse response. Okay, so we are talking about FIR filters. We would assume that the length is m plus 1. So it is defined from 0 to m, capital M. So you would either observe even symmetry or odd symmetry, or the values of the m would be either even, or odd. इस odd को हम एंटी सिमेट्री भी कहते हैं. Right, so that means that you have 4 options. Okay, you can follow even symmetry and m, capital M can be even. You can follow odd symmetry and capital M can be even. You can follow even symmetry and your capital M is odd. You can follow odd symmetry, anti-symmetry, and your capital M is odd. So these are 4 different options available, and these 4 options contribute to type 1, type 2, type 3, and type 4 filters. So I've written down the notes, okay, so that we are able to to understand these things in a slightly easier manner, so that I don't have to write everything. These things I have to write very similar things again and again. So these are not very difficult concept, but important nevertheless. So let's start with type 1 filters. Let's start with type 1 linear phase filters. Type 1 filters would have this relation. H of n would be equal to h of m minus n. So this means what? It is observing what kind of a symmetry? It is symmetric around.
Even.
It is even. It is even symmetry. It's symmetric around m equals to m by 2.
Around m होगा ना?
अभी देखते हैं. यानी से m is equal to 4, एग्जाम्पल ले लेते हैं. अगर आपकी m is equal to 4 है, ठीक है, that would mean h of 0 must be equal to h of 4. यही है. h of 1 should be equal to h of 3 and 2 should be equal to 2. So this becomes the line of symmetry. So the symmetry is around m by 2. Is that clear?
Yes, sir.
ठीक है. So symmetry is around m by 2. So the transformations now, you can write down the transformation. So these can be arbitrary. So this would be h of 0 and this would be h of 4. Okay, and you know the formula for the h of z. It would be h of 0 z to the power 0, h of 1 z to the power minus 1, h of 2 z to the power minus 2, right? So let me have this annotation as well. Right, so h of 2 z to the power minus 2, h of 3, but h of 3 must be equal to h of 0. So h of 0 z to the power minus 4. Sorry, h of 3 must be equal to h of 1. Right, ये देखें ये आपस में ये दोनों इक्वल हैं. So h of 1 z to the power minus 3 and h of 4 must be equal to h of 0 z to the power minus 4. इससे होता ये है कि you reduce the number of multiplications in the realization. जब आप उस filter को realize करने लगते हैं तो number of multipliers आपके कम लगते हैं, and that is very important thing, right? It's a big deal for filter design. If you reduce the number of multiplications by 1/2, it's a big deal. Okay, so you can write down your h of z as h of 0 times 1 plus z to the power minus 4 plus h of 1 times, so instead of 8, instead of these 5 multiplication, you're done with 3 multiplications. ठीक है, अगर बड़ा से फिल्टर साइज है तो ऑलमोस्ट 1/2 कर दिया आपने नंबर ऑफ मल्टीप्लिकेशंस को. ठीक है, इज दैट क्लियर h of z की एक्सप्रेशन?
Yes, sir.
So now we'll take h of z to the power minus 2 as a common.
Yes.
And this is a process जो कि आप फ्रीक्वेंसी डोमेन में बहुत ज्यादा करते रहे हैं. अगर आपके पास 1 plus e to the power j omega है तो आप e to the power j omega by 2 कॉमन ले लेते हैं ताकि आप अंदर वाली जो चीज है उसको साइन और कोसाइन के टर्म में रिप्रेजेंट कर सकें. तो वेरी सिमिलर प्रोसेस, आप z to the power minus 2 कॉमन ले लेते हैं इस पूरे एंटायर h of z से. So you would have terms of h of z to the power 2 plus z to the power minus 2, z to the power 1 times z to the power minus 1 and h of z. ठीक है, and this means now if you want to write down h of e to the power j omega, that is your frequency response, you need to replace z by e to the power j omega, right? And this response, you can see that it is e to the power j omega 2 omega e to the power minus j 2 omega by 2. In other words, this thing, I hope you can realize, if we convert that to e to the power j omega, would be 2 times cosine of 2 omega. सही है ना? And if you replace e to the power j omega in this guy, it would be e to the power j omega plus e to the power minus j omega. It would be 2 times cos of omega. ऐसे ही है ना?
Yes, sir.
and hence h of e to the power j omega can be written as this: e to the power minus j to omega times something 2h of 0 cos of 2 omega 2h of 1 cos of omega plus h of 2, and all of this is real, right? So this is a real function. So we call this response to be hr of omega. We do not call it the magnitude of h of e to the power j omega because the real function can be negative, और जब नेगेटिव होगा तो वो प्लस माइनस पाई की जंप्स ले सकता है, ठीक है? And hence we call it a pseudo magnitude. hr of omega is a pseudo magnitude multiplied with e to the power minus j to omega. So this is a unit magnitude function e to the power minus j to omega. इसका mod 1 है, तो जो mod है वो hr of omega से ही हमें मिलेगा, ठीक है? लेकिन हम इसको pseudo magnitude इसलिए कहते हैं कि it can have variations of plus minus pi, ठीक है? तो exactly magnitude response नहीं होता ये, ठीक है? ये सारा पॉजिटिव नहीं होता, नेगेटिव हो सकता है। तो हेंस अगर आपने एंगल ऑफ ई टू द पावर जे ओमेगा निकालना है तो दिस वुड बी माइनस टू ओमेगा प्लस बीटा, वेयर बीटा would be 0 plus minus pi plus minus 2 pi and so on. That would be because whenever your h of e to the power j omega changes sign, there would be a jump of pi from pi की jump आती है, ठीक है? और जहाँ माइनस पाई की जंप आती है, but if you take the derivative of minus the derivative of this phase, that gives you the group delay. Group delay में बीटा का कोई रोल नहीं है, ठीक है? This goes away. So the group delay here is 2 samples. So you have a group delay of 2 samples इस केस के अंदर, ठीक है? In general इस रिस्पॉन्स को अगर आपने इन जेनेरिकली लिखना है, वेयर m is not equals to 4, you can write your h of z as z to the power minus m by 2 times hr of omega, where hr of omega is given as summation k ak cos of omega k, where ak is given as 2 times, right? 2 times, यहाँ पे देखिए 2 times था, 2 times h of m by 2 minus k, and h of 0 is h of m by 2, ठीक है? a of 0 is h of m by 2, ठीक है? तो k की वैल्यू 0 से स्टार्ट हो रही है, ठीक है? So there was a needs to be corrected, और hence your h of e to the power j omega would be e to the power j minus m j minus j m minus j omega m by 2, that is 1/2 k equals to 0 to m by 2 ak cos of omega k, ठीक है? अब आप यहाँ पर इस एक्सप्रेशन को अगर आप कंपेयर करना चाहें तो यू कैन कंपेयर इट विद m is equal to 4. m is equal to 4 से जरा कंपेयर करें, ठीक है? m is equal to 4 होगा तो आपके पास e to the power minus j2 ओमेगा आएगा, यहाँ पे e to the power minus j2 ओमेगा आ रहा है कि नहीं आ रहा? आ रहा है, ठीक है? k is equal to 0 ले लेंगे, k is equal to 0 में h of m by 2 है, ठीक है? h of m by 2 would be h of h of 2 cos of 0, आपके पास h of 2 की टर्म अलग से आ रही है यहाँ पे, ठीक है? k is equal to 1 ले लेंगे तो a of 1 would be 2 times h of 2 minus 1, 2 times h of 1, 2 times h of 1 times cos of omega, 2 times h of 1 cos of omega की टर्म आ रही है आपके इसके अंदर, ठीक है? यहाँ पे, एंड फाइनली जब k is equal to 2 लेंगे तो आपके पास 2 times h of 0 times cos of 2 omega की टर्म आ रही है. So this matches to this, ठीक है? क्योंकि हमने डिराइव की थी. कोई कंफ्यूजन तो नहीं है इसमें?
No, sir.
Very good. An interesting point about type 1 filter is that h of z is equal to z to the power minus m h of z inverse, ठीक है? इस चीज को देखने के लिए, इसको प्रूव करने के लिए लेट m is equal to 2 एक एग्जांपल ले लेते हैं ताकि आप इस पे कन्विंस हो जाएं, ठीक है, क्योंकि this gives us this allows us to draw very important conclusions. अभी आप देखेंगे, लेकिन आप इस चीज को प्रूव करने के लिए से m is equal to 2 है. If m is equal to 2, आपका h of z क्या हो जाएगा? h of 0 plus h1 z inverse plus h0 z to the power minus 2. ऐसे ही है ना, तीन ही टैप हो सकते हैं. ठीक है, so z to the power minus 2 आप कॉमन ले लें, it would be h of 0 times z to the power 2 plus h of 1 z to the power 1 plus h of 0. सही है. So which is equal to z to the power minus 2 times h of z inverse. यानी अगर आप z को z इनवर्स से चेंज कर दें, तो h of 0 के साथ z स्क्वायर्ड आना चाहिए. ठीक है, h of 1 के साथ z1 आना चाहिए. ठीक है, और h of 0 के साथ कुछ नहीं आना चाहिए. तो दिस थिंग इज नथिंग बट h of z इनवर्स. आपको समझ आ रही है बात? अगर आप h of z के अंदर z की जगह z का रेसिप्रोकल डाल दें, तो ये टर्म वुड चेंज टू z स्क्वायर्ड, दिस टर्म वुड चेंज टू z1 z to power plus 1. यहाँ पर तो z है ही नहीं. ठीक है, so this term inside the bracket is nothing but h of z inverse. तो आपने किया क्या है, आपने यहाँ पे इक्वेट किया है, z to the power minus 2 कॉमन लेने से जो अंदर वाली टर्म है, this becomes h of z inverse. ठीक है, hence it's not a proof, of course it's not a proof, but we can be confident that कि ये वाली जो चीज है it is valid for type 1 filter. So type 1 filter के लिए we would have this property. So this property allows us to draw a very important conclusion. अगर हमारे पास if we have a 0 of h of z, ठीक है, for example z is equal to z naught पे हमारा 0 है ना, ठीक है, so that means h of z naught is 0, then this would mean this relation would mean कि z naught inverse is also a 0. ठीक है, क्योंकि ये दोनों क्वांटिटीज इक्वल है ना, तो अगर z naught के ऊपर 0 है तो 1 over z naught पे भी 0 होना चाहिए. ठीक है, तभी ये क्वांटिटीज लेफ्ट हैंड साइड वुड बी इक्वल टू राइट हैंड साइड. तो जो जीरोस हैं दे वुड अपीयर एज रेसिप्रोकल पेयर्स. ठीक है, अगर 0 हमारा आ रहा है z naught पे, तो 1 over z naught के ऊपर भी हमारा 0 आएगा. ठीक है, what about the poles of the FIR filter? पोल्स का क्या होगा? आर देयर पोल्स हैं या नहीं है?
पोल पे भी ये अप्लाई होगा क्योंकि वही हो रहा है ना, क्योंकि जी इनवर्स भी साथ ही है.
But this is a FIR filter, remember, there are
Yes, sir.
no poles, there are only one pole, all the poles are at the origin. ठीक है, FIR फिल्टर के अंदर कोई नॉन जीरो लोकेशन के ऊपर पोल है ही नहीं. ठीक है, जितने आपके जीरोस होंगे उतने ऑर्डर का पोल आपका z equal to 0 के ऊपर होगा. ठीक है, ओके, सो लेट्स मूव ऑन. टाइप 2 फिल्टर्स. ठीक है, आई होप दिस इज क्लियर. if not, please go ahead with the questions.
Yes, sir, it's clear.
So type 2 filter still maintains an even symmetry, but m is odd now. m odd हो गया. ठीक है, जिसमें लेंथ इवन हो गई. जब आपकी लेंथ ऑफ द FIR फिल्टर इज ऑड, ठीक है, कैपिटल M आपका इवन बन जाता है और आपकी इवन सिमेट्री हो जाती है. इंटीजर वैल्यू के ऊपर आप सिमेट्रिक होते हैं. अब दिस ब्रिंग्स अस अ वेरी इंटरेस्टिंग थिंग. सपोज m इज इक्वल टू 5. ठीक है, और आपने ये वाली इक्वेशन मेंटेन करनी है, ये वाली इक्वेशन मेंटेन करनी है. ठीक है, तो h of 0 would be equal to h of 5. ठीक है, these two would be equal, right? फिर h of 1 would be equal to h of 5 minus 1, h of 4, ये equal होंगे, ठीक है? h of 2 would be equal to h of 5 minus 2, ये दोनों equal होंगे. There is no loner, ठीक है, अकेले loner नहीं है, ठीक है, सारे pairs में है. But ये symmetry, line of symmetry किधर आ गई? So your line of symmetry is at 2.5. So your line of symmetry is at m by 2, ठीक है, which is a non-integer. ठीक है, so this is your type 2 filter. It is still linear phase. ठीक है. So now let's do the same procedure. Let's first write h of z. H of z would be h naught or h5 equal हैं. So I've directly written it h naught times 1 plus z to the power minus 5. h1 or h4 equal हैं. So I've directly written as h1 times z inverse plus z to the power minus 4. h2 or h3 equal हैं. I've written as h2 times z to the power minus 2 plus z to the power minus 3. Now what thing you would take common? इसका आधा, ठीक है, z to the power minus 5 का half, exponent का half. So you'll take out z to the power minus 5 by 2 as a common. That would change things in this manner. ठीक है, h0 times z to the power 5 by 2 plus z to the power minus 5 by 2, z to the power minus 3 by 2 here, plus 3 by 2 here, plus 1 by 2 here, minus 1 by 2 here. ठीक है, so again you have written this in the form कि अब आप h of e to the power j omega बहुत easily लिख सकते हैं. So h of e to the power j omega would be e to the power minus j 5 omega by 2 times 2h0. This would change to, if we replace z by e to the power j omega, this would replace to cosine of 5 omega by 2. This would change to cosine of 3 omega by 2. This would change to cosine of omega by 2. सही है? And hence we have this h of e to the power j omega. इसका group delay interestingly is 5 minus plus 5 by 2 samples. ठीक है, अब इसका angle is minus 5 omega by 2. You take the minus of the derivative, it would be plus 5 by 2. ठीक है, so this although can be realized, but it has its problem. It is difficult to realize. It's not impossible to realize, but this half integer delay causes some problem in the realization. ठीक है, आपको फिर वो नॉन इंटीजर डिले के लिए याद है हमने किस तरह रियलाइज किया था? ठीक है, वी नीड टू कन्वर्ट दैट, एक डोमेन से दूसरे डोमेन में कन्वर्जन रिक्वायर्ड हुई थी. ठीक है, यू वेंट इनटू द कंटीन्यूअस टाइम, वहां पर नॉन इंटीजर डिले के इक्विवेलेंट डिले किया था. ठीक है, एंड देन यू केम बैक टू द डिस्क्रीट टाइम. It has problems. In general, you can write your h of e to the power j omega as e to the power j minus j m omega by 2, right? m आपका 5 था इधर, ठीक है, यहाँ पर आपका m 5 था, यहाँ पर m 5 की जगह m by 2 m आ गया. ठीक है, and then you represent it as, ये जो cos वाली terms हैं, यहाँ पर m आपका 5 है. ठीक है, तो आप इसको लिख सकते हैं 5 minus half omega. sorry, आप इसको लिख सकते हैं, this is 1 by 2, so this is 1 minus half, this is 1 minus half, this is 2 minus half, this is 3 minus half. ठीक है, so you would take values of k equals 1 to 3, and then you would multiply with the cosine term omega times k minus 1 half. That would give you these cosine terms, and then multiply it with bk. Bk must be equal to this guy. ठीक है, bk क्या है? 2 times h of m plus 1 over 2 minus k. ठीक है, that is your bk. ठीक है, where k varies from 1 to m plus 1 by 2. ठीक है, now you can check, counter check. अगर m आपका 5 है तो 5 plus 1 would be 6, 6 by 2 is 3, 3 minus k की टर्म्स आएंगे यहाँ पे. ठीक है, तो 3 minus 1 वुड बी 2, तो h of 2 की टर्म आ रही है, ठीक है, 2 भी साथ मल्टीप्लाई होगा, दिस इज हाइपो। फिर k is equal to 2 पे 3 minus 2 would be h of 1, 2 times h of 1 की टर्म आएगी, k is equal to 3 पे 2 times h of 0 की टर्म आएगी, so it matches, ठीक है। so this is your bk. in addition this formula जो कि हमने टाइप 1 के लिए ड्रॉ किया था, क्योंकि ये भी इवन सिमेट्रिक है, ठीक है, so this would still hold here, this would still hold here, ठीक है। now what would be your h of 1? h of 1 would be 1 to the power minus m would be 1, or 1 over 1 would also be 1, so h of 1 is equal to h of 1. But if we put h of minus 1 here, this means minus 1 to the power minus m would be minus times h of minus 1. So h of minus 1 would be minus times h of minus 1. So remember m is odd, ठीक है, m odd है ना आपका, so minus 1 to the power m. This vector didn't come in the previous क्योंकि आपका m even था, यहाँ पे क्योंकि m आपका odd है, so this gives this relation. So this is a very important relation, ठीक है। इसका मतलब है कि h of minus 1 is equal to minus h of minus 1, ठीक है। The only integer or only value or only real number that जो अपने माइनस का इक्वल है वो क्या है? That is 0. So only number that is equal to minus of itself is 0. This means h of minus 1 must be equal to 0. So you have a 0 of h of minus 1. ठीक है, यानी आपके कॉम्प्लेक्स प्लेन के अंदर -1 के ऊपर 0 आ गया. What does this 0 mean? At what value of omega you have a 0?
pi, omega equals pi.
Omega is equal to pi के ऊपर आपका 0 आ गया. This means कि हाई पास फिल्टर आप नहीं, हाई पास फिल्टर के अंदर ओमेगा इक्वल टू पाई पे 1 चाहिए होता आपका, तो you cannot create a high pass filter out of this type 2 filter, ठीक है, तो हाई पास फिल्टर इज नॉट पॉसिबल, ठीक है. सो अगेन आई सेड कि ये वाला जो रिलेशंस हैं, these they allow us to draw very important conclusions, ठीक है. So let's move on to type 3 and type 4. Formula simple and similar हैं, लेकिन now the even symmetry would change to anti-symmetry. So while type 1 and type 2 were symmetric, even symmetric, type 3 and type 4 would be odd symmetric. That means h of n would be equal to minus h of m minus n, ठीक है, और m must be even, ठीक है, m must be even for type 3. So m even है, this means h of 0 must be equal to minus of h of 4, h of 1 would be equal to minus h of 3, और ये this must be equal to 0 so that it is equal to minus of itself, h of 2, ठीक है. तो बीच वाली चीज must be equal to 0. ये चीज क्लियर है आपको, समझ आइए why this must be equal to 0? क्योंकि
Yes,
loner,
sir.
this is a loner on the line of symmetry, ठीक है, and it
Okay.
must be equal to minus of itself. The only way it can be minus of itself is if it is 0, ठीक है. So your h of z can be written as h of 0 into 1 minus z to the power minus 4, ठीक है, ये एक दूसरे के माइनस है. फिर h of 1 z इनवर्स माइनस z to the power minus 3, ठीक है, और h of 2 तो 0 आना है. फॉर टाइप 3 एंड 4 जो रिलेशन हम पहले देख रहे थे, जिसमें यहाँ पे प्लस साइन था, यहाँ पर नेगेटिव साइन आ जाएगा, राइट, फॉर ऑब्वियस रीजंस, ठीक है. सो नाउ वी कैन मूव फ्रॉम h of z to h of e to the power j omega. So you can see that it is e to the power minus j to omega. अब यहाँ पर this guy is e to the power j to omega minus e to the power minus j to omega, ठीक है. So this is what? This is 2j sin of 2 omega. सही है ना, इसको 2j से डिवाइड करते हैं तो साइन बन जाएगा. सिमिलरली दिस गाय इज वुड चेंज टू 2j sin of omega, ठीक है, क्योंकि बीच में नेगेटिव साइन आ गया. सो h of e to the power j omega is e to the power minus j to omega times j को आप बाहर निकाल लेंगे because you want this to be your pseudo magnitude. So अंदर क्या रह जाएगा जो real आपका part है 2 times h of 0 sine of 2 omega plus 2 times h of 1 sine of omega. Sorry, यहाँ पे 2 omega था. And hence in general you can write it as j times e to the power minus j omega m by 2 summation k equals 1 to m by 2 ck sine of omega k, where ck is written as 2 times h of m by 2 minus k. So this ck is very similar to your ak in type 1. ठीक है? And then you can plug in m is equal to 4 to verify कि ये चीज आती है कि नहीं आती. ठीक है? I hope you would be able to verify. सही है?
Yes, sir.
Yes, sir.
Now अगर आपने इसका फेज देखना है तो इट वुड बी माइनस एम ओमेगा बाय 2 प्लस पाई बाय 2. पाई बाय 2 क्यों आया ये वाला? Because j is being multiplied. j you know is e to the power j pi by 2. ठीक है ना? j किधर है आपके कॉम्प्लेक्स प्लेन में?
Yes, sir.
ओमेगा पाई बाय 2 के ऊपर है ना, 1 पाई बाय 2 पे. ठीक है?
Yes, sir.
अच्छा, प्लस बीटा दिस इज अगेन आपका एच जो आपका सूडो मैग्नीट्यूड है, इट कैन बी नेगेटिव, तो ये बीटा वुड टेक केयर ऑफ दैट. ठीक है? So your group delay would be capital M by 2 samples. ठीक है? Or now let's try to make important conclusions. Remember m is even. h of z is minus z to the power m h of z inverse. ठीक है? h of 1 would be what? Minus, क्योंकि m even है तो z to the power m would be plus 1 h of 1. So h of 1 is minus h of 1. h of minus 1 is again minus h of minus 1. So this means you have a 0 at h of 1, you have a 0 at h of minus 1. So you have what? यहाँ पर भी 0 आ गया, यहाँ पर भी 0 आ गया. This correspond to 0 frequency, this correspond to pi frequency. So not only the high pass filter is not possible, low pass filter is also not possible with type 3. The only thing that is possible, of course, is a band pass filter. Band stop bhi, by the way, nahi possible. If the low pass is not possible, if the high pass is not possible, band stop is also not possible. So the only filter that you can possibly build through type 3 is band pass filter. This by any means, I'm not saying that type 3 is unimportant. Okay, band pass filter is one of the important applications of the filter design. However, type 1 is typically more flexible because it is not restricting anything. It is not restrictive in any sense. Right? Finally, type 4 filter is very similar to type 3 filter. The only difference is your M becomes odd now, and hence the line of symmetry would be, there would be no loner, and hence the line of symmetry would be at a half integer. ठीक है? For example, m is equal to 5 के लिए वही example हमने लिए. So, but these would be negative. ठीक है? Minus से multiply हो जाएगा. So h of 0 would be minus h of 5. h of 1 would be minus h of 4, and h of 2 would be minus h of 3. So you can directly write, right? I've directly written the frequency response as j would come, for obvious reason, e to the power j omega 5 by 2, 2 times h of 0 times sine of 5 omega by 2 plus 2 times h of 1 times sine of 3 omega by 2, 2 times h of 2 times sine of omega 3 by 2. And hence you can write in general h of e to the power j omega to be equal to this guy, where dk would be equal to 2 times h of m plus 1 by 2 minus k, where k varies from 1 to m plus 1 by 2. And you can verify by putting m is equal to 5. So m is equal to 5 अगर आप put करेंगे तो m plus 1 6 हो जाएगा, 6 by 2 is 3, 3 minus k की term आ जाएगी ये. ठीक है? So when k is equal to 1, you have h of 2. ठीक है? Times sine of 1 minus half is 1 half sine of omega by 2. ठीक है? So this is verified. K is equal to 2, you have 3 minus 2 is 1. ठीक है? So h of 1 आ जाएगा इधर, और यहाँ पर आ जाएगा 2 minus half would be 3 by 2. So this gets verified, right? So you can verify by plug in different values of n, and the group delay is here is m by 2. Now, again, final thing before we conclude today's lecture is that it would again verify, would hold to this equation. H of z would be equal to minus z to the power m times h of minus z, and hence h of 1 would be equal to minus h of 1. H of minus 1 is equal to h of minus 1. So there's no 0 at h of minus 1, but there is a 0 at h of 1. That means omega is equal to 0 ke upar there is a 0, and hence you would have a low pass filter of this or this kind. Okay, h of z is equal to 1 minus z inverse. That means you have a 0 at z is equal to z is equal to 1 times h1 of z, where h1 of z is the remaining thing. Okay, so this is your h of z equation. Okay, and hence you can we have used we have elaborated different types of FIR filters. Type 1 is of course the most favored one because it is the least restrictive. But there are cases where you require, for example, a 0 DC gain. ठीक है, डिफरेंशिएटर है, डिफरेंशिएटर का h of आपका क्या होता है, h of e to the power j omega होता है, तो you require a DC gain. ठीक है, तो what kind of filter would be suitable for an ideal differentiator? Any guesses? आइडियल डिफरेंशिएटर के लिए कौन से टाइप का फिल्टर यूज करेंगे आप? you need a 0 at omega is equal to 0, so type 4 should be your preferred one. Type 3 के अंदर तो और भी zeros हैं, that cannot be used. ठीक है?
Yes, sir.
Type 4 would be used, right? Finally, if you allow me 2 more minutes, so this is the last thing. Writing in the generic form for FIR filters, h of e to the power j omega is e to the power j omega m by 2 times e to the power j gamma times your pseudo magnitude, where gamma would be either 0 or pi by 2. So this would be taking care of this j thing. Okay, or this is your e to the power j omega m by 2 is your the thing, or आपका hr of e to the power j omega can be 0 phase or can contribute to plus minus pi. ठीक है, so zeros occurs in the reciprocal pairs. ठीक है, तो ये हमें पता चल गया. Now so for example, अगर आपका एक 0 यहाँ पर है तो इसका रेसिप्रोकल भी यही है, तो आपके पास यहाँ पे 0 आ जाएगा. ठीक है, कोई इशू नहीं है. 0 अगर -1 पे है तो तब उसका रेसिप्रोकल भी -1 ही होगा, 0 वहीं आएगा. 0 अगर j पे है, इसका रेसिप्रोकल क्या होगा? -j. 0 अगर इधर आएगा inside of the unit circle on the imaginary axis, इसका रेसिप्रोकल यहाँ पर आ जाएगा. ठीक है, अगर sorry, I said the wrong thing. Let me take my word back. अगर यहाँ पर 0 है ना, यहाँ पर 0 है, तो इसका एक कॉम्प्लेक्स कॉन्जुगेट 0 होना चाहिए. दैट इज अ मस्ट, क्योंकि आपके रियल कोएफिशिएंट्स आप चाहते हैं. ठीक है, इसके कॉरेस्पॉन्डिंगली एक इसका रेसिप्रोकल इधर आएगा, इसके कॉरेस्पॉन्डिंगली इसका एक रेसिप्रोकल इधर आएगा. सो यू वुड हैव 4 zeros. अगर आपको एक 0 की लोकेशन पता चल जाए तो यू नो कि आपके 4 zeros हैं. फॉर एग्जांपल यहाँ पर 0 आ गया आपका, तो कॉम्प्लेक्स कॉन्जुगेट 0 ने आना है, क्योंकि यू वांट poles and 0 इन द कॉम्प्लेक्स कॉन्जुगेट पेयर्स, क्योंकि आपके कोएफिशिएंट रियल होने चाहिए. फिर इसका रेसिप्रोकल यहाँ पर आएगा, इसका रेसिप्रोकल इधर जाएगा. Okay, so you have 4 zeros, 2 because there must be complex conjugate pairs, and 2 because there must be the reciprocal there must be reciprocal pairs as well. Okay, so we would stop on that note. This is one of the book pictures taken from the book. This is type 1 filter centered around m by 2. This is type 2 filter centered around m by 2. This is type 3 filtered centered around m by 2, which is an integer. This is not an integer. This is type 4 filter centered around m by 2, which is a non-integer. So this is and these are odd symmetric. These type 1, 2 are even symmetric. So I would stop